All right, let's get started. All right, PS10's coming due. Any problems, issues, questions? Okay. We're starting a new topic today. We're going to be, all semester we've been looking at classes of problems, and at first we were looking at algorithms to solve problems, and we started looking at algorithm design techniques. We're now going to move on to the theory of NP completeness, which will take about the next week and a half. And as you might hear the word theory of NP completeness and think this is sort of pie in the sky and not very useful, but it's actually a very crucial thing to know and understand if you're going to be doing much programming. So I think most of you are, so let's talk about it. So here is a classic problem, traveling salesman problem. In a traveling salesman problem, you're given an undirected graph with weighted edges, and you're supposed to find a Hamiltonian cycle. In particular, you want to find the one with the smallest total weight. Now, what a Hamiltonian cycle is a path that starts at some vertex and visits every other vertex exactly once, and then goes directly back to where it started from. So that's what a Hamiltonian cycle is. So if a graph is complete, this one isn't close to complete, but if a graph is complete and has edges between every pair of vertices, there are lots and lots of, it's easy to find Hamiltonian cycles. When it's completely sparse, there isn't a Hamiltonian cycle. But this one certainly has multiple Hamiltonian cycles. And the question is to find the traveling salesman problem. The problem is to find the Hamiltonian cycle with the smallest total weight. So what do you think? Can you look at that graph and tell me? So while you're thinking about this, why might be, we're not so many traveling salesmen anymore, but why might this be an interesting problem nonetheless? Who would be interested in being able to solve problems like this? Yeah?
UPS truck.
Yeah, UPS truck is certainly going to start somewhere and visit a bunch of places and go back where it started from, and wants to make it the shortest in some sense. Least fuel consumed, or fewest miles, or less time, or something like that. So it's an example of an optimization problem that is of great interest. It turns out that no one's ever found an efficient way to do this, which may explain why you're having trouble doing it yourself. So let me just show you. Here's the answer, I think. It doesn't really matter what you consider as a start vertex. It's just a cycle that visits every vertex once and goes back to where it began. And maybe if you can see a way to do it with less weight, you can let me know. Anyway, that's the problem. Okay, so let's keep the traveling salesman problem in mind. We're going to study NP completeness by talking about search problems. And you look at different books, you talk to different people, they all have a different approach to discussing NP completeness. But the book we're using and the slides that I've written talk about it in terms of search problems. So let's talk about what a search problem is. So in a search problem, we get some input. And we'll call that I, an instance I, describes a problem at hand. So for example, you're given a weighted graph. That'd be the problem instance. And you're asked to find a solution S that satisfies some specification. So you might be told, here's a graph, find a Hamiltonian cycle. And specification is a description of what a Hamiltonian cycle is. And furthermore, any proposed solution must be checkable in polynomial time. So we can create really, really hard search problems such that even if you could solve it, I wouldn't be able to convince myself you had given me a solution quickly. So we want these problems to be at least easy enough so that if you were to guess at a solution, there's a fast way to verify whether or not it is a solution. So let's think about the Hamiltonian cycle problem. So that's just finding a cycle. Forget about the weights. Is that a search problem? Okay. Does it fit criteria 1? Are you given an instance of some data? Yeah, you're given the graph. And 2, you're asked to find a solution S that satisfies some specification. So we're asking, I want you to give me back a list of vertices that form a Hamiltonian cycle. Okay? So it meets those two criteria. Is any proposed solution checkable in polynomial time? By polynomial time, I mean O of n to some constant. O of n to the 100th will do. Is there a way to check? You give me a proposed Hamiltonian cycle. How would I check that it really is a Hamiltonian cycle? Okay. So here's that graph. Suppose someone said A, B, C, D, F, E, A forms a Hamiltonian cycle. How do we check that? Yeah?
Could test a slightly different cycle to see if it's faster? Or?
No, I'm not solving the traveling salesman problem right now. I'm solving the Hamiltonian cycle problem. So forget about the weights. I'm just asking you to find a cycle. Yeah?
All the vertexes have been touched and it creates a cycle.
Okay, so first of all, you got to make sure that in the list that you give me, or I've got to make sure that in the list that you give me, every vertex occurs once. Exactly once, except the first and last vertex are the same. So A, B, C, D, F, E, A fits that. Or, A, C, D, F, B, E, A, for that matter, would fit that. But what else has to be true other than it just lists all the vertices? What else do you have to check? Imagine you're grading an exam. Yeah?
You get back to the start position.
That what?
You get back to the start position.
Well, yeah, you've got to make sure it begins and ends with the same vertex. Yeah?
That every pair of vertices has an actual solution.
Right. If you give me A, B, C, D, F, E, A, I have to confirm that, there's an edge from A to B, from B to C to B, and so on. On the other hand, if you give me a solution like A, C, B, E, F, D, A, the vertices that's good. You got the right number of vertices. They each appear once, except the A appears at the beginning and the end, and that's right. But there's no edge from A to C. So if you wrote a program to take in a graph and a proposed Hamiltonian cycle, could you write it? Would it run fast? How hard is it to check that every that consecutive pairs of vertices in a proposed solution have an edge between them? Yeah, really simple. You just look in the graph and see if there's an edge there. So this is an example of a search problem, Hamiltonian cycle. It's easy to check. I haven't told you how to solve it. Most people believe that the Hamiltonian cycle problem is impossible to solve efficiently in all cases. But if you do manage to solve it, there's a way to prove that you have. It's easy. If you have a solution on hand, it's easy to check that it is a solution. Okay. Is the traveling salesman problem a search problem? So now, same issue, but now I want the shortest cycle. Now someone hands me a solution and says, this is the shortest Hamiltonian cycle. Now we've just argued it's easy to check to see whether it is indeed a Hamiltonian cycle. How would you check that it's the shortest Hamiltonian cycle?
Check all Hamiltonian cycles.
Okay, you could find every Hamiltonian cycle in the graph and figure out how long they each were and see if this proposed one is the smallest. But can you do that efficiently?
Nope.
Yeah, it turns out that if the graph is complete, the exponential number of Hamiltonian cycles is possible. So that approach to verifying a solution won't work. Right? So it's hard to say. It's hard to say just off the top of your head. Is there an efficient way, given a solution, is there an efficient way to see whether or not it's optimal. And that's a discussion of that. So I'm going to leave that question open. As to whether or not, what I'm trying to get at is the traveling salesman problem a search problem according to our definition? Or we know the Hamiltonian cycle problem is, but is the traveling salesman problem a search problem? Okay, now, let's see what I skipped over here. Now, you often hear me say that something like, there is a polynomial time algorithm. For example, there is a polynomial time algorithm to sort array of linked lists. There is a polynomial time algorithm to find the shortest path tree of a directed graph with no negative cycles. Okay? You also might hear me say that all known algorithms require exponential time. So all known algorithms for the Hamiltonian cycle problem require exponential time in the worst case. All known algorithms for the traveling salesman problem require exponential time in the worst case. And we're going to divide the world now into problems that we know we can solve in polynomial time, which is every problem we've studied this semester. And then problems for which, as far as we know, they require exponential time. And we're going to consider the ones that require polynomial time solved, good, solvable, and the ones that seem to require exponential time are a problem, bad, too inefficient to use in practice. What does it mean to say that some problem of size n? We're always interested in the size of the problem instance, and that's the size, use n to describe that. What does it mean to run polynomial time? How do you know you have an algorithm that runs in polynomial time? Yeah. Well, check its doubling behavior, but to what end? I mean, what does it mean? Okay, so you look at the doubling behavior, and what are you looking for to know that something runs in polynomial time? Yeah.
Just look at its asymptotic complexity.
Yeah.
What the
Yeah, you look at its asymptotic complexity. So you're just, if you can show that the algorithm is O of n to the c for some constant c, then we can say it runs in polynomial time. And that's why I say every algorithm we studied this semester. Now, there are a few exceptions I didn't really talk about the complexity of, but the vast majority of algorithms looked at this semester run in polynomial time. And we've spent all semester sweating it out. Oh, is it n squared? Is it n log n? Is it n cubed? Is it n? Is it log n? All of those are O of n to 100, say. So they're all polynomial time. You can pick that constant as big as you want. So all this stuff that we've worried about all semester, we're just going to lump them all together as the same. They're all polynomial time algorithms. What does it mean when we say that all known algorithms require exponential time? So if I have some problem and I say the only algorithms that have ever been found for this require exponential time. So in terms, for polynomial time, we said the algorithm had to be O of n to the c. What would be true of every known algorithm if they all are exponential time? Yeah. Yeah, well, not O of c to the n, omega of c to the n. So this says in all cases run in time bounded by a polynomial. This is saying that the lower bound, the worst case at least, is going to require exponential time, where c can be any constant greater than 1, and n is the size of the problem. So you'll see this replayed again and again. We'll just think of polynomial time as good and exponential time as bad. But why should we consider, why I said omega right there. Oh, okay, I know I said omega. Suppose we had an algorithm that was O of n into the billion. That's a polynomial, right? Why is that good? What's good about an algorithm that requires, this is saying it requires into the millionth power. So the worst case requires at least into the millionth. Why should that be considered good?
We care more about doubling behavior.
Well, yeah, we care about doubling behavior, but if it's doubling from 10 years to 20 years, when you double the input size from 4 to 8, that's not very practical algorithm. Would you be, yeah? consider an algorithm like this bad? You know, this is not much different from constant until n gets really huge. Yeah.
Because we care about the places where it gets really huge.
Okay. You know, so what I'm hearing is that, yeah, in the long run, this will become a bit worse than that. But n will have to be really, really unimaginably large before this gets worse than that. Yeah.
I was thinking that if it's a exponential time algorithm, then that generally means you're trying every possibility. Because a polynomial time algorithm, you have some sort of insight into which possibilities need to be tried and which ones don't.
Uh-huh.
And so that insight would be a breakthrough that would lead to better algorithms.
Okay. That's exactly right. So I think it actually uses those words. Well, they're not on the slide, so I'll just repeat what he said. Exponential algorithms are generally, they come up because we're just trying every possibility. We don't know a better way to find the shortest Hamiltonian cycle, so we just find all the Hamiltonian cycles, an exponential number of them, and see which one has the least weight. And that's our solution. So it's brute force algorithms tend to be exponential running time simply because there are too many, there are an exponential number of things to consider. On the other hand, if you can do better than exponential times, you have typically gained some insight into the problem. So going from if you have an algorithm that required exponential time for a problem, and then you find one that takes polynomial time, no matter how high the polynomial is, that represents a breakthrough. Someone has discovered a way of thinking about the problem that no one had thought of before. And what usually happens is, after that breakthrough is discovered, even if the initial algorithm is really inefficient, people can take that breakthrough and run with it and start improving the algorithm and even improving other algorithms until it gets practical. So I'm not claiming that an algorithm like, with that big of an exponent is practical, but it is more interesting than an exponential algorithm because it can be improved on. The other thing is, you just don't see this in practice. You don't see algorithms that are, polynomial time algorithms that are that bad, or exponential running time algorithms that are that good. It doesn't happen in practice. So we're interested in the polynomial time algorithms are the ones that required some insight into the problem to actually work with. Now, I said we're interested in search problems. And I'm going to further divide the world of problems into two other classes, or world of some problems. Decision, search, and optimization. So we talked about search. I want to talk about decision, search, decision, and optimization as well. So a decision problem is just true or false. Is there a solution? So what would be, and often problems, search problems, you can often cast them as decision problems. You can have a variant that's a decision problem. So we talked about the search problem, which is to, given a graph, find a Hamiltonian cycle. What would be a decision version of that? How would you cast that as a decision problem, a true-false question? Yeah?
Is it possible to get a Hamiltonian cycle?
Right, right. So the decision version would be, does this graph have a Hamiltonian cycle? Yes or no? So that's sort of the easiest thing in a way. You're not asked to solve, to find the path. You just ask the cycle. You just ask, is there one? Is there a solution? Okay. Search problem. Is there a solution? If so, what is it? All right. That was the Hamiltonian cycle one. And then the optimization problem. Is there a solution? If so, what is the best one? So what's that similar to that we've seen today? What optimization problem did we discuss? Yeah. Right. Traveling salesman problem is an optimization problem. So you could think of Hamiltonian cycle as being a search problem. The optimization variant is the TSP, and the decision variant is just, you're given a graph, does it have a Hamiltonian cycle? Yeah?
So would depth first search be more of a search problem and then breadth first be an optimization?
Well, it depends what the question is.
So you could look for a path between two nodes and you're doing a breadth first find shortest path.
Okay. Right. So if we have a graph and we want to know, is there a path? That's a decision question, and you can solve that with depth first search. Yeah. If you're given a graph, you want to know what's the shortest path between these two vertices, and it's unweighted, then breadth first search would be a way to solve that, and that'd be an optimization problem. Okay, so you probably have a strong intuition that decision problems are easier than given a particular kind of problem like a Hamiltonian cycle. Solving the decision problem ought to be easier than solving the search problem, which ought to be easier than solving the optimization problem. But what I'm going to show you is that in some sense they're equivalent. They're equivalent in the sense, if all we care about is the distinction between polynomial time and exponential time, they're equivalent. So and the reason I'm doing that is so that we don't have to sweat the details when we get and talk about NP completeness. We don't have to start worrying all the time about whether something's a search problem or an optimization problem, because they're going to end up, the difference doesn't matter for what we're going to be doing. So this is what we just talked about. The decision problem version is given a graph G. Okay, let me back up. I'm going to describe a different decision problem. So given a graph G and a budget B, is there a Hamiltonian cycle with total weight at most B? Right? That's a decision problem. We're not asked to find the thing, we're just asked, does it exist? Then the search version of that is, given a graph G and a budget B, return a Hamiltonian cycle with total weight at most B, or report that there is no such cycle. And then finally, optimization variant of that is, given a graph G, return the Hamiltonian cycle with the smallest weight, or report that there are no cycles. All right, so those are three variants of the same problem. Decision, search, optimization. All right, and let's consider those problems or similar problems. So suppose we have search, decision, and optimization variants of some problem. I'm going to show you, if you have a decision algorithm that runs in polynomial time, so if you can solve the decision problem in polynomial time, I'm going to argue that we can create a search algorithm that also runs in polynomial time. And to make this concrete, we're just going to work with we'll work with those three variants I just showed you. All right? So I'm going to show you how to convert it. So suppose we're asked to solve the search problem. So you're given a graph G and a budget B, and you want to find a Hamiltonian cycle with weight at most B. That's the search problem. Let's assume that we have a solution to the decision problem. Okay? How could you use the solution to the decision problem to create an algorithm to solve the search problem? Yeah?
So it's got to actually solve the problem itself, and so it would just be a matter of like keeping track of the steps taken to solve the problem.
Okay, so you're saying we could look at this, the fact that we can write the decision algorithm down means that we could look at it and see what it's doing.
Figure out how it's coming back.
That it must be, as it's looking at the graph, it must be finding a cycle. So we just need to capture the cycle. Yeah, but I can imagine problems where we could prove that a cycle exists without actually finding the cycle. So let's not assume that it actually finds a cycle. It just has some way of telling us yes or no, there is a cycle. Yeah.
If the decision problem says it didn't find a cycle, then don't even bother searching for
Well,
it.
certainly, if we run the decision algorithm and it says there is no cycle, then the search problem can also report there is no cycle. But what if there is a cycle of a given weight? Yeah?
Imagine that if we have some way to prove that there is a cycle without actually finding it, we would have already been able to prove what the cycle is in order to get that kind of proof.
Well, maybe, but let's not make assumptions about what the proof is like or what the algorithm is like. Let's just use it. Yeah?
It's able to report that there is a cycle. Is it able to report, given a set of data, that is the that is a cycle, or is it there's a cycle on the whole thing?
We're talking about the decision problem and the search problem.
The decision problem, could you use it to test a possibility with the decision problem?
Well, with the decision algorithm, you can't test a proposed solution. All you can do is look at a graph and say yes or no, does it contain a cycle? Yeah.
You kind of sequentially remove edges and then test it again.
Okay. All right, that's the idea. Let me show you what he said. I will illustrate what he said here. First thing we're going to do is run the decision problem. So we ask the decision problem, is there a cycle in this graph of weight at most b? If the answer is no, then this is an implementation of the search algorithm, algorithm for the search problem. If the answer is no, we'll say, the search problem algorithm will say no, there's no cycle. We already said that. Otherwise, for each edge, we're going to remove the edge. So we're going to look at each edge in turn. We're going to remove the edge, and then we're going to run the decision problem and ask, is there a solution in the modified graph? Okay? Now, if the answer is no, what does that mean?
It's part of the solution.
Right. If there was a solution before, and we removed E, and now there's no solution, that edge must have been crucial to there being a Hamiltonian cycle of a given weight. That edge must be part of a solution, so we got to put it back in. On the other hand, what the answer is, yes, even after removing this edge here, there's still a Hamiltonian cycle of that given weight. That edge didn't matter. So we're going to test each edge in turn, and what we're going to end up with in the end is just a graph containing the Hamiltonian cycle. All right, so that just summarizes what I said. Let's see how it works. So we're going to take that edge right there. Now you know, you just have to take my word for it that the Hamiltonian cycle a Hamiltonian cycle of weight 16 is the one I showed you before, which is sort of like one that goes along these diagonal lines. So the edges on the diagonal lines turn out to be one that matters. So I take that edge out and I ask, is there a Hamiltonian cycle of weight at most 16? The answer is going to be no. So we put the edge back. Then we consider that edge 7 and we take it out and we ask, is there a Hamiltonian cycle of weight at most 16? And the decision problem will say what? Yes. So we conclude, okay, that edge didn't matter. Let's leave it out. Okay, so that's what we're left with there. Okay? Now we look at that edge. The decision algorithm is going to say, yeah, well, we know there's a solution now. We take it out, it's going to say, no, there's not a solution. So we put it back in. We consider that edge. We take it out. What's the decision algorithm going to say? Yep, there's still a solution, so we leave it out. And I guess, I'm not sure what I had in mind to keep flashing this up. This just reminds you what the solution is for some reason. Okay? We test that edge, we take it out. And you can see at this point, there's no Hamiltonian cycle at all if we take that out. You know, if you go from A to B, you're stuck. So we put that back in. We consider that diagonal edge. And there is still is there a Hamiltonian cycle?
Yeah.
I don't know. What is the Hamiltonian cycle? Let's say you start at A. You go to B, you go to F.
Yeah, because it's an F twice. So
Yeah, you'd have to go to F twice to get to E. Yeah, there's not even a cycle there.
You would have to start at F for it to be true.
If you start at F.
No, but even then,
Yeah.
even when you visit it twice.
Yeah. All right. Yeah.
If you start at F, go to C, D, A, or sorry, C, D.
Yeah. If you go, it's tempting to go F, C, D. Then you have to go to A.
If a Hamiltonian cycle exists, you can pull it from any node. So
Yeah. It doesn't matter where you start from. If you start at F, you got no choice but to go to C because, well, I guess you do have a choice. But anyway, you go C, D, A, and then we got to choose between B and E. You can't go to both before we get back to F. Yeah.
So we, at the very beginning, we tested A, B, and determined it should be part of the solution.
Yeah.
Then we tested B, C, and we decided to remove it.
Right.
Why do we not have to check A, B again since now the graph has one less edge?
Well, right before we moved BC, we knew that there was a. Okay. Let's go back. All right. So right there, we decided to leave A, B in the graph. So we remove BC and we see there's still a solution. So we leave it out. So what is there that you want to recheck?
Well, why don't we have to recheck A, B?
Well, because right now, we took that edge out and there's still a cycle. So what is there to recheck about AB? AB is in this graph and it's part of the cycle. So there's nothing to make us change our mind. So we leave it out. So let's skip it. I think I was maybe right there. So we take that edge out, no cycle, leave it in. We check that one, that's where we were. No cycle, we leave it in. We check that edge, there's still a cycle of the correct weight, so we leave that in. That edge turns out to be superfluous, and that edge is important, that edge is important, and that edge is superfluous, and now we have looked at every edge and what's left. We've thrown away every edge. If there are V vertices, we have thrown away every, we have V edges left. Yeah?
Is there not a possibility of throwing away an edge that you could actually need should another Hamiltonian cycle not be optimized but still viable for the budget?
The way I described it, no. Because we keep an edge if we show that it's essential to a solution. And then we only remove edges when there's a solution without them. Anytime we throw an edge out, there's, we know that we don't need it to find a solution. Yeah?
Could there not then be two Hamiltonian cycles?
Oh, there could be two Hamiltonian cycles, of the proper weight. This would find one of them.
Okay.
Right. We're not asked to find the best or all. We're asked to find, is there one? If so, what is it? So what's left is just the Hamiltonian cycle, just the edges that are in the Hamiltonian cycle. You can just read the answer off of here. So if the decision algorithm can run in polynomial time, which is going to be some polynomial involving V and E, number of it, the size of the data structure that holds the graph is what we're interested in. What can you say about the complexity of this algorithm to solve the search problems?
It's also polynomial.
Okay, why? It's also polynomial why?
Well, you have to check every edge once, so
Okay.
you're just multiplying a polynomial by a linear, so
Right.
it's still polynomial.
Right, we call that polynomial time decision problem E times once for each edge. So E times complexity of that decision problem is still going to be a polynomial of some kind. You're just multiplying by E. So this is still polynomial. Now, if E is big, that's going to be an expensive algorithm, but I'm just trying to argue that if you can solve the decision problem, at least for TSP, you can solve the search problem efficiently. You can solve one efficiently, you can solve the other efficiently. And you can do similar tricks like this for any other search problem you care to think about. You can basically get the decision algorithm to solve the search problem by repeatedly modifying the input, repeatedly doing solutions, and deciding what belongs, what doesn't belong. Okay, so that's good. Now we have a polynomial time solution to the search problem, to the Hamiltonian cycle problem, with a budget. Let's convert this to, let's do the same trick, produce a solution to the traveling salesman problem. Yep.
And just start with the lowest possible number, like 1 for your budget, and then call the search problem to see if the cycle exists.
Okay. All right. So his suggestion was, okay, you're given some graph, and you're asked, does this graph have, you're given the graph, and you're asked to find the Hamiltonian cycle with the least weight. Okay. So first thing you would do is, let's say you would say, okay, let's see if there's one of weight 1. Let's see if there's a Hamiltonian cycle of weight 1. How would you find that out? Right, you call the search problem. It'll tell you. In fact, it'll give you the Hamiltonian cycle if there was one of weight 1. What if the answer is no, there isn't one of weight 1? You try 2. All right? That will tell you yes or no. What if the answer is no, you try 3. And then we try 4, and then we try 5. And the answer keeps being no, 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 no. When do we stop?
So when it says yes.
What if it never says yes? If there is no Hamiltonian cycle, it's never going to say yes.
Maybe try running an unweighted version first.
Okay? Yeah, we can do that. Yep.
Could you also text the limit it to the maximum weight possible?
Okay, you can put bounds on the solution. So if you know that if there are V vertices, there are going to be V edges in a Hamiltonian cycle. So you could take the smallest edges in the graph, add their weights together. That's the bottom, that's the lower bound on the weight of a Hamiltonian cycle. And what would be the upper bound?
The V largest.
It'd be the sum of the V largest. So now at least you have an interval to look through. So then you could start with the lowest and work your way up to the highest and see if the answer, as soon as the answer becomes yes, you found the solution. That'll work, but there's a problem. It's exponential.
Takes a very long time.
The problem is it requires an exponential number of steps. You could have a simple graph. Imagine you had a very small graph with some edges of weight 1 and some edges of weight 1 trillion. Okay? It doesn't take many bits to describe that graph, but how many steps is it going to take? If you start with the smallest possible Hamiltonian cycle and work your way up to the largest possible. And it's going to take 1 trillion steps, or let's say there's 10 vertices, 10 times 1 trillion steps. We get from 10, which is going to be the smallest, up to 10 trillion, which is the largest. Yeah?
Could you do a permutation and do it through the possible sets?
No, we don't need to do a permutation. So the problem is, it's similar to a problem that you studied before in 2420. Yeah?
Could we use a binary search?
Use a binary search. So the problem is, if you've got to count from 1 to 1 trillion or 1 to 10 trillion, that's an exponential number of steps compared to the size of the problem. That's what we're worried about. But if you do a binary search, in that interval, so you start in the middle and you say, is there a graph of, is there something with a weight less than, is there a cycle with a weight less than or equal to this? If the answer is yes, then you focus your attention on the bottom half of the interval, otherwise the top half. By doing that binary search, it makes it run in polynomial time. Yeah?
Can you describe how you're getting the lower and upper bounds again?
Okay, so if there are n vertices in the graph, we find the n lightest edges in the graph.
Just the n. So is it the n lightest that cause a Hamiltonian cycle? Or?
No, we know that the Hamiltonian cycle will have n edges. And so if we find the n smallest weights in the graph and add them up, no Hamiltonian cycle can have a weight less than that. Right. I'm not saying that the n weights are going to form a cycle or anything. They just give you a lower bound. The same thing with the upper bound. We take the n biggest weights and add them up, and no cycle can be larger than that. So the binary search is just a trick to make it so it's not exponential running time. Because without that, if you had to do a linear search, then very small, you have graphs that just take a few bits to describe, which take a tremendously long time to run, this algorithm. But the binary search saves us. So that's the whole trick here. This is all this is saying here. So what we've shown now is that if you have an efficient, i.e. a polynomial time solution to the decision problem, you have a polynomial time solution to the search problem. And if you have a solution to the search problem that runs in polynomial time, you can solve the optimization problem in polynomial time. So the takeaway from that is when we're discussing NP completeness, and I'm saying that as we do it, we're proving things about search problems, and I slip up and I start talking about an optimization problem, it's no big deal because they're all sort of equivalent if we're moving in this world where all we care about is the distinction between polynomial time and exponential time. So we don't have to be too careful about sticking strictly to search problems. Yeah.
So just with the first example that using the binary search on this optimization problem, going from 1 to 1 trillion, why does that become exponential? The way I think about it is it's basically 1 trillion times that you call the search algorithm, which is polynomial. So why isn't it just 1 trillion times the cost of the search, which is still a large number, but to me that's the nearest thing.
Okay, so what you have to look at is the size of the problem. How many bits does it take to represent the trillion that shows up as the weight of the edge?
Just log of the trillion.
Yeah, so it's about 40 bits. So every one of those trillion edge weights is going to take 40 bits in the data structure. Okay? What happens if you double them from you double the length from 40 to 80 bits? So you had a graph with all these 40-bit edge weights in them, and now you increase them so they're 80 bits long. What happened to the running time of our algorithm just now? In fact, let's just add a single bit to each edge weight. So our edge weights that were 40 bits long are now 41 bits long. Before, we had to iterate from 0 up to 2 to the 40th. Now by adding a bit to each edge weight, we go from 0 up to 2 to the 41st. So our representation grew just by a few bits, but the running time doubled. That's an exponential algorithm. You have to focus, you don't focus on a trillion as a constant. A trillion is part of the input, and it takes some number of bits to represent. And as that trillion grows, the running time of the algorithm grows exponentially. Okay? The difference between 1 million and 2 million is just 1 bit. But the time it takes to loop from 1 to 1 million is half of the time it takes to loop from 1 to 2 million. All right? It becomes vitally important to keep in mind we're trying to express the complexity of our algorithms in terms of the size of the data. And that comes, it comes naturally when the data is an array and its length is n. And I've found through the years that when the data is a number, as in when we talked about encryption, the distinction between the magnitude of the number and its size gets lost. That's what's important here, is the size of the input, not the magnitude of the input. Any other questions? Okay, so we got search, decision, optimization. We're going to focus on search, and we're going to investigate that further. So let's take a break and we'll do that. All right, so we just finished talking about search problems, and there's our definition again. So we're going to call a search problem. The key thing about the definition of a search problem is that any proposed solution must be checkable in polynomial time. We're not requiring that the problem be solvable in polynomial time. That turns out to be a key question. We're just requiring that any proposed solution must be checkable in polynomial time. So let's look at some examples of search problems. So what about searching an array? You're given an array of integers and an index x, you're given an array of integers and a value x, and you're asked to find an index where x is stored, or a -1 if there's no such index. All right, so that's a That's a search problem. It's easy to check a solution. If someone says x is stored at index 20, you just go look and see if x is stored at index 20. So that's trivially a search problem. In fact, if we can solve the problem in polynomial time in the first place, it's going to be, efficient to check. You just resolve it. Okay. Factoring. You can think of that as a search problem. You're given an integer n, and you want to find its prime factors, n1 through nk. So what's the check? What's the efficient check to see if that is the prime factorization of the integer? Yeah? You multiply them together and see if you get n back. Plus, you need to check that the factors are actually prime. And there's a polynomial time algorithm to do that, so we're good. That's a search problem. Right, here's one, independent set problem we never talked about. The independent set problem is you're given a graph, undirected graph, there are no weights, and an integer n, and you're supposed to find a subset of the vertices of size at least n, such that there's no edge in the graph between any of the vertices in the set. Okay? So maybe a picture would be good here. So if you have a graph like this, you have A, B, C, D, E, F. Does this thing contain an independent set of size 2? Okay? So are there two vertices that don't have an edge between them? Yeah, A and D. Is there an independent set of size 3? Are there 3 vertices that don't have any edges between them?
There are 2 sets.
Okay? So ADE is one set. ADF is another. And actually there's BCE, BCF. Is there one of size 4?
So one can have an edge between them, but do they pairwise have?
No, pairwise, no edges.
Okay, so BCF works, but BCE doesn't.
Oh, you're right. You're right. Thank you. Yeah, BCF works.
Okay.
BCE doesn't. But ADE works in AEF. So it looks like there's 3. Can you find one with 4?
No.
Okay. So that's the independent set problem. That's a decision problem. Why? How would you check a solution? Someone says BCF is a solution. How would you check it?
Check to see if there are edges between B and C, C and F, and D and F.
Yeah, you just have to look at every pair. There are only n squared pairs in the solution, and you make sure there's no edges between them. And plus you make sure that only valid vertices are in the set. That's easy to check. So independent set problem is a search problem. Here's the satisfiability problem. And this one looks kind of weird, but it actually has, turns out to be really crucial in things like fields such as proving that hardware is correct. The idea is you're given, just think of it's just a Boolean expression here, where plus stands for or, and then the bar stands for not, and then there's the implied and of all these things. So this is x or y or z, and x or not y, and y or not z, and so on. And the problem is find a way to assign true and false to the variables x, y, and z, such that the overall expression becomes true. So in real applications of this, you might have thousands or hundreds of thousands of variables and massively long expressions, and it may boil down to if you can find a way to make this statement true, it means that this piece of hardware is correct. That's a really high-level sketch of how it would be used. So can you do it? Can you make this thing true?
No, there's no solution.
There's not a solution. I have one on my slide, so one of us is wrong.
Okay, here's why I say there's no solution.
Yeah.
You have x or y or z on the far left, and you have not x or not y or not z on the far right.
Right, but x can be true and y can be false.
Okay.
If these were ANDed together, you'd be right.
Yeah, okay.
Okay? So here's a solution. We make x true, y true, and z false. So since x is true, this is true, and that is true. So that takes care of all that. y is true, so it picks up this guy. And z is false, so it makes that one true. So then, it's basically got to make each of these things true, and then together you get true. Right? So that's the satisfiability problem. Is that a search problem? Is it possible to verify a solution in polynomial time?
Yeah.
Yeah. You just saw me do it. You just do something like I did. You take the first variable and go see which expressions, which of these it makes true, and then see which ones y makes true, which ones z makes true. Make sure they all got turned to true. Not so bad. Now there are a couple of variants. This way of writing a Boolean expression is called conjunctive normal form. And anything that you can write as a Boolean expression can be expressed in conjunctive normal form, which is the ands of ors, where there are no more than 3 variables per clause. Okay? So call that a clause. No more than 3 variables each one. So that's a perfectly general way of describing any kind of Boolean expression. And we'll call that 3-sat. So this is in 3-sat form. There's also 2-sat form, which is not perfectly general. There are things you can't express in 2-sat format, where you'd only have, you couldn't have x plus y or plus z. Everything would have to look something like that. Okay, so that distinction will become important in a bit. So the 3-sat variant and the 2-sat variant of the satisfiability problem. Very famous problem. Okay? The Hamiltonian path problem. I've already been talking about that. Your book calls it the Rudrada path problem. I think because Rudrada, I guess the authors feel like Rudrada got cheated out of this because he studied it first. The Hamiltonian got named after it. But you won't find that name anywhere else that I can tell. Hamiltonian is a lot more, I don't believe it's Alexander Hamilton. Okay? So given a graph G, find a path that visits every vertex exactly once. So we've already discussed that to death. So that's a search problem. Traveling salesman problem, where there's a budget or a goal W. Find the shortest Hamiltonian cycle of weight at most W. That's a search problem. We talked about that. This is a famous one, the Euler path problem, which is what I want to find is a path that traverses every edge exactly once. Okay, so rather than, you can visit vertices multiple times, but you want a path that crosses every edge exactly once. And the story is this problem came from, I think it was a German city where there were think of each of these things as a bridge over a river. So maybe there's a river that runs here and it forks, something like that. So like Pittsburgh. And the question was, is it possible to take a walk and cross every bridge exactly once? And it turns out Euler studied it and generalized it and found a way to describe it mathematically. But this particular graph here has no solution. But it's a search problem because if someone said, I've got a solution, it'd be easy enough to check it. You just take the solution and follow it along and make sure that you never use an edge more than once and that you eventually touched every edge. So that's a search problem. Knapsack problem we've discussed. That's a search problem. Sort of. Technically speaking, when we did the knapsack problem, we were trying to find the way to steal the most loot. That sounds like an optimization problem. But how would you cast it as a search problem? Yeah.
So is there a way to steal this much loot?
Yeah. So rather than say asking find a way to steal the most loot, you would ask find a way to steal X amount of loot. But again, we're not sweating the difference between search and optimization. Okay, subset sum problem. Looks like, this is simple enough to describe. You're given a set of integers and some m. And just ask to find, is there some subset of this that adds up to 20? No? Is there?
Yep.
3, 8, and 9. Okay. So that's a search problem. Easy to verify. If someone says 3, 8, and 9 add up to 20, that's easy to check. And it's, you know, you have to check that 3, 8, and 9 belong to the set and that they add up to 20. That's easy. Shortest path problem. So here I'm going to describe it. This isn't what we saw with Deichler's algorithm. This is more general. Is you're given a weighted graph G and vertices U and V. Find the shortest path from U to V that doesn't use any edge more than once. That's how you describe the shortest path problem when there are negative cycles. You sort of deal with the negative cycles by saying you're not allowed to use an edge more than once. We're looking for the shortest simple path. So that's not a problem that Dijkstra's algorithm can solve, or any of the algorithms we study can solve. That's the generalized shortest path problem. And here's the interesting thing. Some of those search problems we just described are known to be easy. And how do we know that they're easy? And remember, easy means polynomial time. So how do we know that minimum spanning tree is easy? Yeah?
Someone solved it with polynomial time?
Right. We know we've got a book with a polynomial time algorithm in it. Therefore, it's easy. 2-set. There's an algorithm for that runs in polynomial time. The shortest path problem, if there are no negative cycles. That's known to be easy. Dijkstra's algorithm. Independent set problem that I just showed you, if the graph is a tree, known to be easy. There's a neat dynamic programming problem. I didn't have time to go over it, but the very last bit of my slides on dynamic programming talks about that problem on trees. And so it's solvable in polynomial time. The Euler path problem. There's an algorithm to solve in polynomial time. On the left, we have problems that are believed to be hard. And I'll tell you why, I'll eventually tell you why they're believed to be hard, but the thing I'll tell you right now is no one has ever found a polynomial time algorithm for any of these. That's what they all have in common. To date, they haven't been solved. So 3-set is believed to be hard. Now, what's the difference between 3-set and 2-set, which is known to be easy? Yeah?
You could just fit one more variable inside the...
Right. The things you're ORing together in 3-set, you can OR 3 variables together, OR their negations. 2-set, only 2 at a time. Okay? And that apparently makes a huge difference in whether the problem is solvable or not in polynomial time. The traveling salesman problem is believed to be hard. Minimum spanning tree is known to be easy. Now, I'll put them next to each other for a reason. They're sort of similar if you think about it. What's similar about the traveling salesman problem in the minimum spanning tree? Yeah?
Trying to minimize the weights on some graph.
All right, you're trying to minimize the weights, the weight of some path in the graph. And furthermore, what do those paths have in common? Yeah, they visit every vertex once. Now there's this thing about you have to, with the traveling salesman problem, you got to close off the, there's an extra edge you add at the end to close the cycle. But basically, they're both computing spanning trees. Okay? It's just that the spanning tree, if you ignore the closing edge, the traveling salesman problem finds a spanning tree, but it's a particular kind of spanning tree that isn't, you're not allowed to have arbitrary forks in it. And so if you're allowed to create a general tree as your spanning tree, you can find an efficient algorithm for it. If it's required to be a cycle, no one's ever going to solve it. The shortest path problem, if you don't allow negative cycles, or if you don't allow negative edges, or if it's on a DAG, whatever. Efficient solution. Generalized shortest path problem, no one's ever found a way to solve it efficiently. Independent set problem, if your graph is a tree. Good. If it's not a tree, best known algorithms require exponential time. Hamiltonian path problem. Don't know how to do that efficiently. Euler path problem. You can do it efficiently. What's the difference there? What's the difference between the Euler path problem and the Hamiltonian path problem? They're actually kind of similar. Yeah?
One checks the vertexes and one checks the...
Right. So this visits every edge. This visits every vertex. knapsack problem. Even though we found a dynamic programming solution, I didn't point it out at the time, but the dynamic programming solution requires exponential time. And the subset sum problem. That's also, I shouldn't say it requires exponential time, it's believed to require exponential time, both of these. Yeah?
What's the difference between subset sum and knapsack without repetition?
This is it's a version of the knapsack.
Okay.
Okay, now if that was all there was to it, that we got problems known to be easy and problems believed to be hard because, well, what's a reason you could give for believing them to be hard, given what I've told you so far? What evidence is there that these are hard problems?
Technically none.
Well, it's just practical evidence.
Just the only solution to be found in
Right. Lots of smart people have been trying to solve these problems for many years. You know, people have been programming computers since 1946. And we have managed to solve a lot of problems, but despite the fact that these are of, a lot of these problems are of really important practical use, to UPS or whatever, no one's been able to solve them. So you could just say, okay, the fact that no one's ever been able to solve them means that probably in the future no one will be able to solve them either. Because people, you start to think we're not going to have some breakthrough. But you might think, okay, maybe most of them are hard, but maybe one of them will solve in the next 10 years. You might think that. But there's more evidence than that, much more evidence than that those problems are intrinsically hard and probably don't have an efficient solution. So what they have in common is that, first of all, none of them had been proven to require exponential time. So there's no mathematical proof that they're hard. There's just sort of empirical evidence. But they all have something in common. They all, if one of them requires exponential time, they all do. So if one of you went out and proved that the Hamiltonian path problem requires exponential time, so if you could come up with some proof, similar to the fact that we proved that comparison-based sorting requires n log n time, if you could prove this problem requires exponential time, or that problem requires exponential time, it would imply, for reasons we haven't discussed yet, that all of them require exponential time. So it's not like someone's going to solve one of them and the rest are just going to remain unsolved. Okay? Because if one of them has a polynomial time solution, they all do. And furthermore, I could make this list be 1,000 or 10,000 problems long. And all the problems on that list what they would share is that if any of them has a polynomial time solution, they all do. And we'll explain why. But why is that pretty good evidence? Why does that make your feelings stronger that it's unlikely that you're going to find a fast solution to any of these? Yeah.
Maybe just the sheer number of different kinds of problems and stuff.
Right. There's the sheer number of problems and the sheer number of programmers and mathematicians that have worked on this over the years. You would think that if there was some breakthrough to be had, because if you could make the breakthrough on any of these problems, you'd have them all. That's not a mathematical argument, it's just sort of an empirical observation. But it's considered very unlikely that any of these problems can be solved fast. But stranger things have happened. But it would be, every now and then you will read about that someone has proven that all those require exponential time. And to date, those proofs have all turned out to be wrong. I can believe that someday someone will prove that they all require exponential time. What would be really earth-shattering is if someone found a fast solution to these. I got to make sure. Okay, just making sure I started the recording. Okay, so to discuss those problems on both sides, I'm going to define two sets, P and NP. So P is the set of all search problems that can be solved in polynomial time. Okay, so so forget about verifying at polynomial time. We just want to be able to solve it at polynomial time. So we're just asking, is there an algorithm that you give it a problem instance and it spits out a solution, and the running time is O of n to b, where b is a constant and n is the size of this problem instance that's going in. Okay? So what's an algorithm that belongs to P? What's a search problem that can be solved in polynomial time? Yeah?
Or the Euler path.
Right, the Euler path problem is a member of P. So if we go back here, the problem's known to be easy. Those problems belong to that set P. Problems that and the way you show that something belongs to that set is you find an algorithm for it that runs in polynomial time. So that's P. Then there's a set NP, and that's just a set of all search problems. So it's just another name for what we're calling search problems. And remember, that means the solutions can be verified in polynomial time. So to be in that set NP, there has to be some algorithm B that takes in a description of a problem and a proposed solution and spits out true or false. Is it a solution or not? And that thing has to run in polynomial time. So V of IS has to run in polynomial time where n is the size of I. Okay? Those are our two sets, P and NP. So which of these sets here, which of these problems belong to that set NP? All of them. P is a subset of NP. If you can solve it, and if you can solve it in polynomial time, you can certainly verify in polynomial time. So P is a subset of NP. So and all these can be verified quickly. So all of these problems belong to NP. Only some of them are known to belong to P. So that's the difference between P and NP. Now, what do you think the N in NP stands for?
Non-deterministic.
Okay, he spoiled me. Okay, if he hadn't said that, what do you think most people think N stands for?
Not.
Not. And they think NP stands for not polynomial. No. For technical, historical reasons, there are multiple ways to describe the theory of NP completeness. Traditionally, it was described in terms of non-deterministic computers, which don't exist. It was sort of a theoretical, it was a way of describing it. It's perfectly valid. Nowadays, it's more common to describe it in terms of verification algorithms. So it doesn't mean non-P. It just NP stands for non-deterministic polynomial time. All right. So here's the billion-dollar question, the trillion-dollar question. What is the relationship between those sets P and NP? Is P a proper set of NP? If it is, that means that there's some problems, there are problems that are members of P, but there would also be problems from NP that are outside of P. So is P a proper subset of NP? That's one possibility. Or, that didn't work out, are they the same set? So if they are truly different sets, then all the problems on the left of that list I just showed you are in this region. And the problems on the right are in that region. And if they really are different, none of those problems will ever be shown to have a polynomial time algorithm. So this is the world most people believe we live in. The world where the two sets are different, or P is a proper subset of NP. This is the world where all those problems that are believed to be hard, suddenly we find a solution for them and discover that P and NP were the same all along. That would surprise most folks if we live in that universe. But right now it's not known. And so that's the question. Does P equal NP? Do all those hard problems have solutions or don't they? So if P equals NP, it means that all search problems, meaning if you can verify a solution in polynomial time, you can solve it in polynomial time. If P is not equal to NP, it means that there are some search problems, like the ones on that list on the left, that require exponential time. Okay, it's the you become really well known if you were able to solve this, just to decide this. Lots of people have tried, but no one has succeeded in answering this question. All right, so I've sort of set up the thing. We've got these two sets, P and NP. We want to investigate whether or not they're the same. There's one more set we need to talk about, and that's the set of NP complete problems. And just informally speaking, a problem is NP complete if it is among the hardest problems that belong to the set NP. So the set NP contains some easy problems, such as Euler path problem. It contains some harder problems, such as factoring. And it contains the hardest problems, such as the Hamiltonian cycle problem. Hamiltonian cycle, turns out, is NP complete. It is in a subset of NP that contains the hardest problems in NP. Factoring it's an open question whether it's among the hardest problems or not. So the NP complete part, we need to define NP complete so we can have a more intelligent discussion about that question, P equals NP. So what we're going to do now, and continuing into next time, is develop the machinery we need to describe what it means for a problem to be NP complete. And to do that, I need to describe to you what a reduction is. And informally, a reduction is just implementing one algorithm in terms of another. Solving a program using a library is a reduction. Right? When you write a program using some API, you are reducing the problem of, reducing the task of solving your problem to the task of turning it to a problem that's solved by the library. So it's, I just have a lot of students that freeze up when they see the word reduction and when they see this diagram here. It's just a sort of a formal way of describing programming, solving one thing by using something someone else wrote for you. It's an everyday thing. Reductions are an everyday thing for programmers. They're not weird and esoteric. So this is what we want. We want an algorithm for some problem A. So A is a search problem. We want an algorithm for A. What comes into the algorithm is a description of the problem at hand. So you're given a graph and a target, a budget. And what comes out the other end is either you're told there is no solution. Suppose A is find a Hamiltonian cycle with a weight less than 50. You can say, no, there is no such Hamiltonian cycle with weight less than 50. Or what could come out would be a solution. Here's a Hamiltonian cycle with weight less than 50. That's what we're after. We just want an algorithm for a problem. Problem A. Now, what we have to work with is an algorithm for some other problem B. So how can you, if you've got, and maybe A and B are somewhat similar, and you've got this idea that, okay, I've got this library method B, I want to use it to solve this problem A. But unfortunately, A takes slightly different input format than B does. And the solution format of B is slightly different than the one I want for A. So what would you have to do? What do you have to do when you want to use a library method or a library class? And it's going to be very useful, but what the data you have to give it is slightly different than the data it wants, and the output that it gives is slightly different than the output you want. What did you as a programmer do? Yeah.
You just convert it to something that algorithm for B can use, and then that's algorithm B.
Right. You take the input, you take what you want to deal with, you convert it some way. You run a little code on it, you modify it so it's good input for A. You feed it to A. I'm sorry, for B. You feed it to B. B solves the problem. It gives you some output that's not quite what you need. So you convert that, and you get output that's in the right form. And that's a reduction. And so symbolically, this is how we'll describe it. what's going in inside the dotted box, which is algorithm for A, is we take input that's intended for A, we modify it to obtain input intended for B. Then we run B on that data, and B either says, I have a solution, or it says there is no solution. If there's no solution to this modified input, we report there was no solution to the original input. And if there is a solution to the modified input, we run H on it, which is just converting it into a form that we can report as our answer. So that's just a picture of what you do when you use a library method. You take your data, you modify it in some way, you run the library method, you take the answer it spits out, modify it in some way, and give that as your answer. That's a reduction. All right, there are lots of lines and boxes, but that's a reduction. Questions? Yeah?
Would you consider Dijkstra's a reduction?
Well, you have to have two algorithms to talk about.
Dijkstra's reduction on like a depth first search using the provider.
Well, no, the question would be let's say,
Or would you actually have to call like the depth first search for your computer?
yeah, let me describe it, let me do it in a different way. How would you reduce the problem of, suppose you have a sorting algorithm, and your problem is to find the largest element in an array. How could you use a sorting algorithm to your benefit? So the sorting algorithm is algorithm B. This doesn't fit exactly because sorting is not a search algorithm, but I'm just trying to get something simple here. So you've got a sorting algorithm, that's B. The problem you're trying to solve is find the largest element in an array. How would you use the sorting algorithm? Yeah.
You could just plug in the input to that sorting algorithm with a comparison and then graph whatever the
Yeah.
result is.
So you take your array, you'd feed it in here, do nothing to it. F would do nothing. B would sort. Out would come a sorted array. And what would H do? We just take the last element of the array, which is the largest, and report that as the answer. That's a reduction. Just writing one algorithm in terms of another. Okay. So here is an example that uses problems that we've talked about. Let A be the problem of finding a Hamiltonian path between two vertices in a graph. So a Hamiltonian path is one that visits every vertex but doesn't go back to the beginning. It just starts here, wanders around, hits every vertex once, and ends somewhere. That's the path. Cycle has to be closed. So if we let A be the problem of finding the Hamiltonian path, and B is the problem of finding a Hamiltonian cycle, we want to see if we have solved the Hamiltonian cycle problem, could we use it to solve a Hamiltonian path problem? In other words, does A reduce to B? So the question becomes, let's say you want to find out, is there a Hamiltonian path in this graph? How could you use a Hamiltonian cycle program to answer the question for you? How could you trick Hamiltonian cycle into finding a Hamiltonian path? Yeah.
Maybe add a temporary edge between the first, like your start one and the destination.
Okay, I'll go back to you. The thing I forgot to mention is the Hamiltonian path, there's a start and an end point as inputs. So we're asked to find the Hamiltonian path between A and B. And your suggestion is what we do is we stick an edge between A and B, ask is there a Hamiltonian cycle, and when we get one back, we remove that edge, and that's the Hamiltonian path. That almost works. We'll see why it fails in certain cases. And it turns out your idea almost works. What we have to do is add another vertex with these edges. And if this thing has a cycle, then all we have to do is take the solution we get back and remove the yellow edges from it, and we've got a path to that. That's a reduction. It's not a complicated thing. You can solve one problem, you can solve the other in this case. So we'll continue with this next time. We'll see why the easy solution of putting a yellow edge from A to B doesn't work, and continue on.